Today we'll talk about electric current, or what is sometimes in normal parlance referred to as current electricity. Electricity or current is one of the most common forms of energy that we see around us, be it the workplace or the form of energy that powers a lot of devices around in our homes. In the previous two chapters, we talked about static electricity, or electricity that does not flow, or it is static, it stays put in one place. Whereas electric current is generally the term that refers to the phenomenon of the flow of charges. So how do charges flow, or what makes them flow? That's something that we'll explore in this chapter. To start with, let's clear up on a few of the basic concepts. Consider a small area. Let me consider a conductor in the form of a cylinder, and I take a normal. To the cross section of the cylinder. Now, if I look at this place microscopically, I should be seeing some charges moving in this direction, and there will be a few charges that will be moving in this direction. Say some of the positive charges might be moving in this direction due to a potential difference, or there might be a few negative charges that might be moving in this direction. So I can define if charges that are moving in this direction as the charges Q positive and the charges moving in this direction as Q negative, then the net charges is given by the total positive charges minus the total negative charges. So this flow, which is the net flow of charges, is what constitutes current or electricity. Now if you pay attention here, Q net is proportional to time. It's proportional to time. The more the time I allow, the more the number of net charges that will flow across. In that case, I introduce a proportionality constant called current, which helps me remove the proportionality sign, and I get I equals Q net by time. So if I is positive, it is described as current in the forward direction, and if I is negative, then it's described as current in the backward direction. So I, as a function of time, is basically defined as the ratio delta Q by small amount of time delta T, when delta T tends to 0. So we define electricity as the ratio of charges flowing through a conductor over a period of time as time tends to 0. So that gives us the unit of electricity, which is charges over time, which would then be coulombs per second, or you can abbreviate it to coulombs per second. Coulombs per second is a unit that in modern physics is named as ampere. Ampere is the standard unit of electric current. It's named in honor of Andre Marie Ampere, the brilliant French mathematician and physicist who was one of the founders of the science of electromagnetism. Now, ampere can range across several hundreds and thousands of amperes, as is the case when lightning bolts are seen during a thunderstorm, or it can range to microamperes in the case of nerve impulses. So amperes can range from several 100,000 amperes to something as small as in the range of microamperes as seen in the nerve impulses of the human body. We'll next study about electric currents in conductors. Electric currents occur when electric charges are subjected to a certain force, and that's something that we do know. And generally speaking, in nature, microscopic particles are inert or neutral, hence they are not charged, whereas the upper layers of the atmosphere, especially the ionosphere, has charged particles or ions. Even in bulk matter that we see around us, like solids or liquids, generally the molecules are so densely packed that the electrons are not confined to individual nuclei. Rather, they are relatively free to move within the bulk matter. And that's very clearly seen in the case of metals. In the case of metals, there are certain electrons that are not bound to any particular nuclei. Rather, they are free to move within the bulk of the conductor. Similarly, in the case of electrolytic solutions, you have both positive and negative ions that are freely able to flow. So in that case, we define that in metals, a current is the result of electrons or negative charges that move. Whereas in the case of electrolytic solutions, current is the result of the movement of both positive and negative ions. So previously we discussed that current or electricity, especially in metals, is due to the flow of negatively charged electrons. So metals could be like aluminium, iron or copper. And in the case of electrolytic solutions, a simple electrolytic solution is salt water or sodium chloride solution, or it could be copper sulfate solution. You mix any salt with water and what you get is electrolytic solution. And in the case of electrolytic solutions, we discussed that electricity or current is due to the flow of both positively and negatively charged ions. Now let's consider two scenarios. Let's consider scenario 1, wherein I have a cylindrical conductor which is just sitting out there in the absence of any electric field. So what's happening at a microscopic level? You have electrons within this metal piece. You can imagine it to be a piece of iron. The electrons inside this iron piece are moving. And why are they moving? They are not moving due to the presence of an electric field, rather they are moving due to thermal energy. They are moving due to the thermal energy gathered from the surroundings. So each electron is moving in a randomized direction. Hopefully, let's say this particular electron hits an ion and then it bounces back in a totally random direction. It could continue to keep moving left, or it could bounce back in the direction it came from, or it could bounce 90 degrees upward. It could be any random direction, and millions of electrons are engaged in this randomized movement. So what's happening? Effectively speaking, the net number of electrons that are moving in this direction at any point of time is almost equal to the net amount of electrons that are moving in this direction. Similarly, the net amount of electrons moving in this direction is equal to the net amount of electrons moving in this direction. So obviously, they're all cancelling each other out, and hence there is no net flow of charges, which means no current. Now let's consider scenario 2. I take the same piece of my cylindrical iron, and this time round I introduce an electric field by introducing a pair of discs, one a positively charged disc at one end and a negatively charged piece of disc at the other end. So which means I am effectively introducing an electric field, let's say E, which emerges from the positive side and terminates at the negative end. Now what happens? Now the electrons will all be subjected to a force that pulls them in the direction of the positively charged electric disc. So for a brief moment, these electrons will all rush in this direction and they will neutralize the positive charges on the electric disc. So briefly, there is an electric current, and then there is no electric current. So when I introduce the two discs, a positively charged disc at one end and a negatively charged disc at the other end, briefly you will see a flow of electrons towards the positively charged disc, which means there is an electric current in effect. But this is so brief because once the electrons that have rushed here and neutralized the positive charges, there's no more reason for electrons to keep rushing to this end of the plate, because the electric field ceases to exist. And that means there was a brief electric current and then there is no electric current. But suppose I keep these two plates connected to some source which keeps replenishing the positive charges. It keeps replenishing the positive charges continuously, which means for every positive charge that's neutralized by an electron, I introduce one more positive charge. Then what I'll see is a continuous flow of electrons along the length of the ion conductor, which means there is a continuous flow of electricity.